Welcome to Science Turnaround, a new compilation of case studies presented by Hovion scientists. Our multinational team partners with global customers to help deliver life-saving and life-changing medicines for patients all over the world. Most of the projects are complex and challenge us to innovate. In this case study series, we will share how Hovion's expertise, scientific rigor, and out-of-the-box thinking allowed us to see alternative scenarios, accelerating progress and improving results. Let's start.
Hello, my name is André Cruz from Hovion R&D, and I will take the next few minutes walking you through a case study showing one of the broad range of benefits achievable through the implementation of process analytical technologies in pharmaceutical processes. In this specific case study, I will go through a real-life example of the use of PET to debottleneck our processes by replacing QC methods and therefore reduce QC workload. First, an overview of the case study. We have a fluidized spray drying process to isolate a pharmaceutical compound down to a specified water content range. To meet these quality criteria, the in-process control strategy includes a sample collection every 30 minutes for water content determination by Karl-Fischer titration. This leads to a significant QC load, and since the Karl-Fischer method takes around 1 hour to be performed, it cannot keep up with the sample generation rate. So this further causes delays in the IPC feedback and hinders optimal process control. To overcome this bottleneck, we implemented a PET water content determination method using near-infrared spectroscopy, which allows for fast IPC response time and enables optimal process control. Furthermore, since NIR analysis does not require any sample preparation, as is complemented with chemometrics and the review by exception workflow, the shop floor operators are independent in executing the IPC workflow, further allowing productivity gains by reducing the QC burden by over 900 samples per year. For viewers less familiar with fluidized spray drying, it is a drying process where a solution or a suspension is fed to a nozzle that atomizes the feed into a drying chamber with a co-current gas stream which flash dries the droplets into particles. The resulting particles are then carried by the gas stream into the fluidized chamber for further controlled drying and afterwards separated from the gas in a cyclone. The specific spray drying detailed in this case study has a high throughput and run continuously for 2 days. With the sampling every 30 minutes required by the in-process control strategy, for every batch, up to 90 samples are collected. So the large amount of samples and the execution time of the Karl-Fischer method lead to a significant QC burden and a delay in the IPC feedback. To overcome this bottleneck, a NIR method was developed. NIR analysis can be performed inline by measuring powder properties directly in the process stream without the need of sampling, or offline by taking a sample and analyzing the product afterwards. For the NIR method developed and explained in this case study, data from both strategies was used. So the greatest advantages of using NIR rely on the low sample preparation requirements and the low complexity of the analysis procedure. Taking these two advantages into consideration, it is possible to implement a spectroscopic method that can easily be performed by any trained operator and still have a method that performs faster than the reference method. In this case, the entire NIR analysis takes no more than 10 minutes. And please note that these 10 minutes are measured for the offline approach, as the inline will be performed always faster. To develop a quantitative NIR method, it is necessary to develop a multivariate model which quantifies the required analyte, in this case water, against the absorbance of the spectra at selected wave number regions. To develop such multivariate or chemometric model, the NIR signal needs to be correlated against a reference value. In this specific case, the calibration is performed by correlating the NIR spectra with the Karl-Fischer titration results, as the latter is defined as the reference method for the calibration. To develop an accurate, specific, and robust NIR method, we use state-of-the-art multivariate modeling tools and mathematical filters to obtain a model which is sensitive to the desired analyte and reduce the interference that sample physical attributes or environmental and equipment variability may induce on the spectral profile. Using the data acquired for this case study as an example, the raw or unprocessed spectra, depicted on the left-hand side of the slide, show high variability between the different NIR equipment used for acquisition. This is removed or minimized after applying the mathematical filters as depicted on the right-hand side of the slide, maximizing the spectral variability related with the chemical response of the analyte. So, in a nutshell, the multivariate modeling is the key ingredient to achieve the required method performance. Furthermore, successful multivariate modeling can be improved by selecting spectral regions where the analyte of interest is most responsive. As depicted on the right-hand side of the slide, the regions highlighted in red were selected as it is known that water is highly responsive on those regions. The final NIR model show good linearity figures as depicted on the left-hand side of the slide. For validation, the NIR method is tested against an external and independent dataset, from which the reference Karl-Fischer values are known. These reference values are used to evaluate the NIR predictive performance. As you can see on the right-hand side of the slide, the NIR model is performing adequately as no major drifts are observed between both NIR and Karl-Fischer values. The implementation of this NIR method promoted a significant reduction on QC workload while enabling production to have faster in-process control response time, which enable an optimal process control strategy and early detection of process challenges. At a last stage, the implementation of the inline tool further improves the analytical workflow as it does not require any sampling.
Thank you for listening. Wondering if your projects can also achieve better results? Contact Hovion's experts today.